In this video, we're going to look at an example of what we call a mixing problem. So, in this problem, we have a tank which contains 20 kilograms of salt dissolved in 5,000 liters of water. So that's what we see right here inside of the tank. Brine, which is another word for salt water, which contains 0.03 kilograms of salt per liter of water, enters the tank at a rate of 25 liters per minute. So that's what's happening up here. There's water being pumped into this tank, which has a different concentration of salt. If you do the math, the original concentration of salt is exactly 0.004 kilograms per liter. And so we're pumping in much saltier water. So we're adding in much saltier water into this tank here at a rate of 25 liters per minute. Then inside of the tank, there's some kind of a fan or something like that, which is, rotating quickly to completely thoroughly mix the salt solution together so that all of the water inside of the tank, as soon as it enters the tank, is completely and perfectly mixed. This is an ideal situation. Of course, in the real world, perfect mixing doesn't occur instantly, but we're going to assume that it does for the purposes of this problem. Then, at the same time, water is being drained out of the bottom of the tank. And the water that's being drained out is the same concentration as the water that's already in the tank. So at the beginning, the water that's draining out is the very low salt concentration that we started with. So water is coming in that's very salty, water is leaving that's a little bit less salty. So the salt concentration in the tank is actually rising. And so the question that we're trying to ask here is, after 30 minutes, how much salt is actually in the tank? Okay, so this sounds like a complicated question, but we're going to approach this from a differential equation standpoint. We're going to write a function which represents how much salt is in the tank at a particular time. And we're going to call this y of t. So y is the amount of salt at time t. Now, we don't know anything yet about this function, right? We don't know, what it really looks like. We don't know what form it's going to take. But we do know that the derivative of y with respect to t, if we take dy dt, this is the amount of change in our variable here. So this is the rate of change of the function y. That's how much salt is entering at any particular time t. So this we can actually write a differential equation to represent. We can write an equation that defines this value here based on what we know about the water that's coming into the tank and the water that's leaving the tank. So if we know the amount of salt entering the tank and the amount of salt leaving the tank at every time, we can write our differential equation here. The rate in minus the rate out. So if we have the rate at which salt is entering the tank and the rate at which salt is leaving the tank, we have, when we subtract them, the total rate of change of salt in the tank. So let's see if we can figure this out. How quickly is salt entering the tank? Now we just want salt itself, not water here. So what we know is that 0.03 kilograms are coming in for every liter of water, and there are 25 liters of water coming in every minute. So the rate in is going to be the 0.03 kilograms per liter multiplied by the 25 liters per minute. When we multiply these, we have liters in the denominator and liters in the numerator. These guys cancel each other out, and the units that we're going to get here are going to be kilograms per minute. And that's exactly what we want here. We're talking about kilograms of salt entering the tank per minute. So if you multiply this, 0.03 times 25, you're going to get exactly 0.75 kilograms per minute. Okay, that's a constant, right? The water entering is exactly the same at all times, so the rate of salt entering is a constant. All right, the rate out is going to be a little bit more tricky to figure out here because the water that's leaving is just leaving at whatever concentration is in the tank at any given time. Well, we know that Y of t is the amount of salt in the tank, and there's going to be a constant amount of water in the tank. It's always going to be exactly 5,000 liters because every minute we have 25 liters in and 25 liters out. The total remains constant there. So the actual concentration of water leaving here is going to be the amount of salt in the tank, which is Y of t, divided by the number of liters in the tank, which is 5,000. That's going to give us our kilograms per liter here. So the rate out, let's switch colors here. The rate out is going to equal the Y of t that we don't know, divided by 5,000. This is kilograms per liter. There we go. So this is the kilograms per liter part of this question here. We need to multiply this by the 25 liters per minute so that we can get how many kilograms per minute are coming in. And fortunately, the amount leaving the tank here is just another constant here. We're going to multiply by 25 liters per minute. And so once again, the liters in the denominator and the liters in the numerator cancel each other out. Our result is going to be kilograms per minute here. So we have Y of t times 25 divided by 5,000, which is equal to Y of t divided by 200. Kilograms per minute. Okay, so we now know the rate in and the rate out. We can write a differential equation, dy dt equals this value minus that value. I'm going to need to do some erasing so I have space to solve this differential equation. Okay, so we have dy dt, the total rate of change of salt with respect to time here. It's going to be the rate in, which is 0.75, minus the rate out, which is Y of t over 200. Now I'm just going to write y so that the variables are a little bit easier to track as we go through here. Okay, so now I have my differential equation. My goal is to try to solve this. So I've got dy dt over here, and then I've got a function that only involves the variable y on the right-hand side. What I'd like to do is move all the y variables to be with the dy, and move the dt to the other side so that I can integrate. First, I'm going to combine these into a single fraction here. 0.75 is the same thing as 3 over 4, or 150 over 200. So we're going to get 150 minus y over 200 here. Now I can divide both sides by the 150 minus y to move that to the other side, and multiply both sides by dt. So divide by 150 minus y, we're going to have 1 over 150 minus y times dy is equal to 1 over 200 times dt. We have now separated our differential equation so that all of the y's are on one side with the dy. There are no t's, so we don't have to worry about putting them with the dt, but if there were any, we could do that as well. Okay, so now we're going to take an integral on both sides of this equation. Apply an antiderivative here and here, and see what comes out. All right, on the left side, we have 1 over a constant minus our variable here. This is going to turn out to be a natural log. You can use a quick u substitution if that makes you more comfortable, with u being 150 minus y. That'll show you when you use the chain rule part that you'll get an extra factor of -1. So we're going to have negative the natural log of the absolute value of 150 minus y is equal to the antiderivative of the other side. We have just a constant here, So we're going to get 1 over 200 t plus our constant of integration. Once again, doesn't matter where we put the plus c, we just want to have only 1 for simplicity here. Okay, so we have now started to solve our differential equation. Another thing that we know, which I've now erased, unfortunately, but which you could scroll back in the video to find, is that initially the amount of salt in the water is 20 kilograms. Another way to say that is that y of 0 is equal to 20. So we have y of 0 equals 20. That means if I plug in t equals 0 to both sides of this equation, the y value should be exactly 20. So that means that negative natural log of 150 minus 20 is equal to 0 plus our constant. So this gives us what the value of our constant is equal to. Our constant is equal to negative the natural log of 130. All right, so that means that our actual equation that we're going to use is when c is equal to the negative natural log of 130. Again, the absolute values don't actually matter here. So the equation that we have, that we're working with now, sorry to keep erasing, but there's lots of writing to do. Is going to be negative natural log of 150 minus y in absolute values is equal to 1 over 200t minus the natural log of 130. Okay, now I want to solve this for y, so I'm going to do that. You can multiply everything by -1 here, so that you have the natural log of 150 minus y is equal to positive natural log of 130 minus 1 over 200 times t. Now take e to the power of both sides to cancel out this natural log. We're going to have the absolute value of 150 minus y equals e to the power of the right-hand side here. Okay, again, when we have addition or subtraction in the numerator here, we can break the right-hand side up into 2 separate exponents. We're going to have e to the natural log of 130 times e to the negative 1 over 200t. E to the power of natural log of 130, the e and the natural log will cancel, and the right-hand side is just going to be 130 times e to the negative 1 over 200t. And the right side, the left side is still 150 minus y in absolute values. Now, in order to keep solving for y, I need to deal with these absolute values now. The good news is the right-hand side here is guaranteed to always be a positive number, right? 130 times e to this power. 130 is positive. E to any power, no matter what that power is always positive. So the right-hand side is guaranteed to be a positive number here. It's never, ever going to be 0. It's never going to go negative. So the sign of the right-hand side is always the same. That means that the sign of the left-hand side should also always be the same. And since y of 0 starts out at positive 20, that means that 150 minus 20 here, positive number. This value on the right-hand side is also never going to cross 0. 150 minus y must always be positive, no matter what the value of y is. So because of that, I can erase the absolute values at this point here. That was a little bit complicated, the reasoning there. So feel free to check out the writing in the textbook. It's a little bit more convincing. You can take some time to understand exactly why it is that I can erase the absolute values at this point. But we're guaranteeing that 150 minus y is always a positive value, so it's equal to its own absolute value. We don't need those absolute value bars. So now I can solve for y by adding y to both sides and subtracting this exponential expression here. We are going to get, when we do that, that y is equal to 150 minus this exponential expression, 130 times e to the negative 1 over 200 t. Now, e to the negative 1 over 200t, as t gets larger and larger, this expression here is going to get smaller. So we are taking 150 minus a smaller and smaller value. That means that the expression here for y is actually going to get closer and closer to the number 150. As t goes toward infinity, the y value approaches 150. And so what that means for this problem is that if you were to continue this tank mixing problem, eventually the amount of salt in the tank would approach 150 kilograms. And that would be a perfectly mixed tank at that point. But what we are actually trying to solve, what we are actually trying to answer is how much salt is in the tank after just 30 minutes. So that is going to be y of 30. Y of 30 is what you get when you plug in t equals 30 here. So we have 150 minus 130 times e to the negative 30 over 200. And so if you plug this right-hand side into your calculator, you're going to find that it's approximately equal to 38.1 kilograms. So after 30 minutes, the amount of salt in the tank has increased from a starting value of 20 kilograms to a value of 38.1 kilograms. It took half an hour to get there. And so that is a tank mixing problem. A little bit complicated at first. The differential equation that you end up solving looks a little weird. We haven't seen one that looks quite like this. But in the end, you have a value, you have a function that describes the exact amount of salt in the tank at all times, a function that we couldn't have found in any other way. All right, so this is the last video for section 9.3. I hope you enjoyed this introduction to differential equations. If you like these kinds of problems, if you're interested in doing a wider variety of problems like this, I suggest that you take the course Math 230 here at Highline. You are technically qualified for it as soon as you pass Math 152, although I would kind of recommend actually that you take Calculus 3 before differential equations. It's totally okay to go right to this class. All right, that's going to be it for this section, so I will see you all in class on Monday. Thanks very much.